So, hello everybody. I'm really excited to be here and to talk about how browser makers are making browser fast. And I will use Firefox Quantum as an example of how browser vendors are modifying the browser to cope with the 21st century. Most of the things that I'm about to say is also valid for a lot of other browsers, but I'm taking the example of Firefox Quantum. So I'm Jean-Yves Perrier. I'm part of developer outreach at Mozilla, and I have a Twitter account. So the story starts a little bit with how a computer works. So at the core of the computer, there is a processor. And processors have evolved over the years very quickly. Initially, in the 70s, 80s, 90s of last century, there was something called the Moore law that was basically saying that every 2 years or every 3 years, your computer becomes twice as fast as previous, which was very convenient for people making programs and browser in particular, because you do nothing, and 2 or 3 years later, your browser is twice as fast. It's kind of free lunch. Lately, at the beginning or second decade of this 21st century, people are seeing that processors are not really doubling the speed anymore each 2 or 3 years. It's still a little bit true for the high-end processors, but in fact, it doesn't really matter for the web, because we are no more in a point where we want the web to run only on the high-end processor. Most of the time, you want it to run on such device, and it's not the latest, the most powerful processor in it, because else the battery will just last 5 minutes. So processors has found a different way to increase their calculation power, and it's by having more cores, so more processing power in parallel. And the difference here is there is no free lunch. Program has to adapt themselves and to make use of these multiple cores, of this concurrency that is now available. At the same time, for browsers, what we want browsers to do has changed over the years. So at the beginning, it was just displaying a document, and even in 2005, if you were able to put a few images and making rounded corner or on the box, you were a top-notch developer. It's not the case anymore today. And what we want today is to have HD videos running with transparency effect, with rotations, and you want all this to run at 60 frames per second. You want all this to run on your virtual reality headset, which means that, in fact, you need more than 60 frames per second, because if you want, with a virtual reality headset, not to have motion sickness, you need at least 80, if not 100 frames per second in order to achieve this. In order to cope with this, browsers had to adapt. They were designed in the 80s, end of 80s, and mostly at the beginning of the 90s. Even if they have evolved over the years, it's not the same architecture that is able to run the modern web. So this story today is about telling you what browser vendors are doing in order to make your website, your web application faster, even without you having to do anything. The browser is a user agent. And in 2008, we used this robot for the launch of Firefox 3. It's a friendly robot. But of course, over the next decade, it looks a little bit clunky. Is it still the user agent that we want to have on the web? So the question is, what a modern browser is doing in 2018. Sorry. First part is, how does a web browser work, and especially the rendering engine? So this is quite important to understand a little bit, so that you understand what the change is are happening. So the first thing is your browser is downloading pages. It requests handle on the web, and it gets HTML, the JavaScript, the CSS files, and just parse all this into an HTML parser, the JavaScript engine, the CSS parser. And what it does is to generate the DOM of nodes. So each time you modify the DOM of nodes, the whole process starts again, not the downloading, but what follow up. So with the CSS, the first things to go in a rendering engine is a style engine. The style engine take the CSS and apply and define what rules are applied to each of the boxes. It doesn't apply them yet, but it just defines what are the set of rules that match each element of the DOM. When you have this, you add all the media. So the images, the videos, and you can know the size of the images, the size of the videos. And when you have this, you have a phase that is a layout, which is, in fact, defining where on the page will be displayed each of the boxes. You have several layers, because they can be on top of each other, but you don't know yet what is inside the layers and which layer is winning. The next step is a paint. So this is to apply texture on each of the layers that will define, OK, this texture is the video, this texture is the image, this texture is just a background or some text. From this, then you have to define which pixels are visible. This is the next step and the last step. That is a compositor. And then you go to your page on the screen. And each time you modify the DOM, you have to go through this process again. For years and years, browsers have already optimized this part by only redesigning or redrawing the part of the page that are actually modified when you change the DOM and not the whole page. But this is really the big and important element. At Mozilla, in order to improve this, we wanted to test new algorithm, and we wanted especially to work on parallelization. So what we have done, first we have created a new language called Rust. Rust is replacing little by little the different part of Firefox written in C++ by this language. And this language has been designed to make the writing of codes that can be executed on multiple core, on multiple threads, much easier, with less errors than C++ and so on. That's really important because a lot of people are contributing to the code, and even if most people are really good programmers, they do error, but you can also get patches for programmers that less experienced, and they will not do the basics common errors. We created then an experimental engine, an experimental browser called Servo. It's written in Rust. It has algorithms that take parallelism and that allow us to check if these algorithms are working very well. And also, it has no significant UI. It's not a real browser. It's something to test if the ID we have are good or not. And finally, and this is the most important part, Servo can break the web. The web is a very complex piece, and there is a lot of special cases with special CSS properties and so on. And in fact, to test the algorithm, you don't want to have to write the engine in all the detail first. You want first to validate that in the good case, in the easy case, you get the speed improvements that you wanted to have. So we did this Servo, and we developed a lot of things on it. At the same time, we wanted to solve several other problems. So Firefox had a stability problem. We noticed over the last few years that it has a lot of crashes, and we were wondering why. It has an old theme. So like the robots that is just looking old, by just having an old theme, when the UI in OSs has been improved, it feels slow. And also, there was a lot of cases where, in fact, the user interface was freezing. It's called UI yank. And finally, we wanted to to have the new algorithm. So we launched a project called Quantum at the beginning of last year, and we decided we want to make a quantum leap in performance and in the way the websites are rendered. There are several things that has been done, but the first thing, and I want first to thank my colleague Lynn Clark, who has drawn this amazing drawing. I'm absolutely unable to make any drawings that looks readable by anybody. So she's doing a lot of these drawings. She's writing blog posts explaining how a browser is working. There will be a link later that allow you to have more information. So the first things that we have decided to do is to change our style engine. So the style engine, as I said, takes the different CSS properties, look at the selectors, at the specification, and in fact, for each of the boxes, define, OK, these properties with this value apply to this one. For example, the background color, or the text color, the font, and so on. This is something that has to be done to each and every boxes. So this is, at first sight, something that can be used very easily with parallelization. And so we tried it in Rust on Stylo. So basically, we had several processes, several threads, that takes part of the tree and makes the calculation. And of course, it's not that easy because first, you don't have one thread, one process per element on the page because there are sometimes several thousand of them. So you have to give chunk of the page to each of the processes. So that means that some of these processes are just idle at some point because there is nothing happening. They have finished their work, while others may be extremely busy. So there is a very big, complex algorithm here that allows the different threads, the different processes to still work from the other when they are idle. So with this, we created and we validated that the new way of doing styling in the browser is, in fact, much, much more efficient. But that was only the first step, because this is in Servo, in the experimental browser. We needed to sort out all the detail and to integrate this into the real browser. And integrating a new style engine in a browser, it's a little bit like doing heart surgery, but with a person that is still conscious. You want the browser to continue to work. You don't want to suddenly have no new release for 1 year, 2 years, while you put all the wire together. So we took the stylo, the Quantum CSS, with the parallelism. We integrated with the rule tree from Firefox. And also, we took the style sharing cache from Chrome and Safari. So the style sharing cache just memorize things you have already calculated, because sometimes on the page, a lot of nodes have the same ancestors and the same values, so it works pretty well. In fact, it wasn't working that well anymore, because lately, with all the pseudo classes and so on, it became more complex, and there are less of these elements that are there that were cached. So we modified the style sharing cache in order for it to work again. And then we just transplanted Stylo into the browser. And this happened last November in Firefox 57, and we got, for this part, a very, very large improvement in speed. So Stylo is the first technology transfer from Servo. It's not the first part of Rust inside the browser. And it is solving a problem that is called embarrassingly parallel problem. By definition, style engines are doing something that can be massively parallelized. And of course, when the page is simple, you see little improvement. When the page is very complex, you see a lot of improvement. Browser has another challenge. Each time you click somewhere on the browser, there is an event handler going on and firing and executing some code. And you want to be sure, if you want to have 60 frames per second or 120 frames per second, that all that's happening on the main thread, and especially these handlers happening, is no more than 16 milliseconds, or 8 milliseconds for 120 frames per second. So that means that you have to go out of the main thread as soon as possible. Because while you are in the main thread, you cannot handle the next event. So the next event when you are scrolling a page or when you are clicking and so on. Initially, browser had everything on the main thread. And little by little over the years, they start to take things out. So first of them is the video decoding that is happening now most of the time on the graphic card itself. There was the plugins also at this place, Canvas Worker, and several others. But what is quite interesting is we have another piece of computer power on the browser. That is a GPU. Oops. The GPU is designed for games, is designed for the operating system where you have a lot of calculation to do on a lot of data. The same operation on a very large amount of data. And it's very, very efficient for this kind of things. It's very efficient for gaming. On the browser, we have this kind of operation. One of them is the compositing. So the last bit of the calculation where you have all the layers and you have to define which one are visible or not. It's the same operation most of the time on a lot of data. So we decided in 2016 to offload the composition to the GPU, and we did it. And it improved a lot. At the same time, a little bit later, in fact, we noticed that the crashes just increased. We had a lot of crashes. And in fact, it wasn't the browser itself that was buggy, it was the drivers that were buggy. So the crashes were mostly happening on Windows, and for example, Mac has very few crashes because there are far less type of driver, far less types of graphic cards, and less bugs. So we decided last year to solve the crashes by having the GPU, the graphic drivers loaded in a different process. So the process crash, the browser detects its crash, it restarts it, and then it works without using the GPU for this part. So you don't have all the speed improvement of the GPU, but you don't have the crashes either. So that's a way we had to mitigate the bugs in graphic drivers. So the compositor is the first part that went to the GPU at the beginning of last year. Another part is a painting. So the painting is to take a texture and to apply it to a surface. It's called rasterization. And we want to do the same, offloading it to GPU. And this is a project called WebRender. It's not yet finished, it's in progress. This is the ultimate goal. I don't know when it will be finished, because if you ask the management, they say very soon, and if you ask the developers, they say, oh, in several years. So it's somewhere in between. Meanwhile, we decided that, OK, even if we don't send it to the GPU, we can remove it from the main thread. So we have what we call off-main thread painting, just a thread for the painting. And this has been done in Firefox 58, which went out in January. So basically, we create a set of instructions, the display list, that is applied to, assigned to the layers, and then we send it to another process that's rasterized, which is the actual painting operation, and then sent to the compositor that is in its own process or on the GPU. And that way, as soon as the rasterization is no more on the main thread, so that means that you can create the next display list and so on. So we remove the bottleneck. It's not as perfect as having everything on the GPU. We still sometimes lose frames when it's go a lot of changes, but much less often. It's no more the rasterization the problem. So this landed in Firefox 58, and there is an improvement coming, the next version in 2 weeks, where in fact we discovered that the display list, we don't need to recalculate it each time. It was simple, but it's not the most efficient. So now we have heuristic in place so that we don't recalculate the display list or the whole of the display list each time. So until now, we have mostly seen replacement of pieces of the browser. And in fact, if you want to have a browser that is efficient, that feels quick, responsive, you need to consider it as a system as a whole. Because yes, you can have a very efficient style engine, but maybe the bottleneck is somewhere else. So we changed the way to do development and to prioritize the development at Mozilla by having the motto measure all the things. Then we triage, we prioritize, and we remeasure. And we applied this, and we still apply this to fight yank, so freeze in the UI. And there is a collection of 30 blog posts by Asian Gary that explain all the changes that happen all over the place. It's going a lot of details. And he coins the name death by a million cuts. We found bugs where we had to fix 10 bugs, and suddenly we get back a lot of time. Each of the bugs individually in the individual fix were just shaving 1 millisecond here or there, but no significant difference. But the 10 together were giving a lot of differences. So one of the things that we changed is the way we were doing scrolling. It's not specific to Firefox at all, and it has been pioneered by Apple, and it's called checkerboarding. When you scroll on your screen with a mouse or with the finger, you never want the scroll to stop. But sometimes it goes too quick, and you don't have the time to calculate what to present to the screen. So you present a default value, and people, instead of being confused, scroll less quickly. The data appear, the images appear. And initially, it was a checkerboard. That's why it's called checkerboarding. So the overall speed is not better, but the feeling is completely different. Another big thing that we have changed is what we call IPC, inter-process communication. So it's known for a long time that when you communicate, for example, with a disk, it takes a lot of time, and you don't want to do this on the on the main thread. It's the same when you communicate with another process, especially if it's synchronous communication. You don't want to do this on the main thread. So we fight synchronous communication, and we wanted to have as many asynchronous communication at all. And this is where we did a lot of measure and so on. There was, for example, 2 people working for 6 months on the cookies, because cookies were needed a lot of synchronous communication. They rewrote completely the cookie mechanism in Firefox. And in fact, it was 25% of our blocking on inter-process communication. And on big website, when it was fixed, like Facebook is making several write several times per second to the cookie store. In this website, like Twitter or Facebook, we were able to win in the order of the second in the time we made to display the page. There was other offenders, like plugins, but plugins are gone today, or the traditional extension on Firefox, the Zool extension also were an offender there. So we had to decide to stop having that. There are plenty of other things that we have done. For example, we have changed some algorithm. They are still efficient, but they were already efficient, but in fact, sometimes they were not making good use of the cache. So we keep an algorithm with the same complexity, but that works better with a cache, for example, and suddenly you have an improvement of your performance on complex pages with the same complexity of the algorithm. Also, the garbage collection, so the parts that take back the memory, has been changed. Instead of having to do a complete sweep, or we can now do an incremental sweep, so we take a bit of the memory, we stop because we have only a few milliseconds, and then we continue later. So that means that the memory grows a little bit, but when the browser is idle, it goes back to normal. At the same time, we notice that memory that is used towards the end very quickly and so on is the one that usually is released very quickly, and what you have done, I don't know, 2 hours before, usually you will keep it until you close the browser. So we also have changes, these kind of things. And the last thing is we try to remove all timers in the interface. Timers are really, really bad. At first look, it looks very nice because you delay the execution later. But in fact, you don't control when the execution will happen. And when the timer will fire, not only it will fire on the main thread, but maybe it's a moment that is important for something else. You have no control. So in fact, the web platform, and this can be used also on website, we have now request idle callbacks. Let's say fire this or do this when the main thread is free. We also did things like throttling background tabs. So if it is in the back, it's less important. But of course, if there are music playing in the back, you don't want your music to stop. So we are very, very defensive here, and we process with experimentation. And finally, we redesigned our user interface. So the feeling of the user interface is something really important. So the look has to look modern, and it doesn't change the speed. It changes the perception of the speed. One thing we change is every animation now is happening on the GPU. It's happening through CSS. We had in the previous interface still animation done in JavaScript, and they were causing a good deal of the yank. So that's really important, that animation not in JavaScript on the main thread. We change a bit the structure of the user interface, so it's quicker for the user to find elements. It's not quicker in speed proper, but it's quicker for the user. So with all these things together, we have now a new engine. And it looks still a user agent, still a nice robot, but it looks much more modern. And it's not finished, in fact. Quantum was released in November, but already the two next versions of the browser had more improvements. The web render is coming soon, or at some point. We have other ideas to improve things. And in general, browsers are still evolving. It's not the end. It's a new beginning, because it's the first time we have now this power of having a massive parallelism on a browser. So I want to thank you to here. Also, you can help by installing Firefox nightly, by reporting problems, especially when your application or your website is much slower in Firefox than in another browser. This interests us, because it's difficult to have real-life data. Each time we do a commit, there are 2,000 hours of tests going on a farm of computers. But it's tests. It's not real-life things. So if you file a bug, say you can give help by reproducing it, engineer will be very happy. Spread the word. We want as many people to use as many browsers as possible, Firefox if possible too, because competition is good. That's a way we improve speed. And Firefox Nightly Twitter account is where to stay informed. Thank you.